So we are now moving on to chapter 4, which is the fundamental research issues in methods and behavior research. The learning objectives are to define and distinguish among construct validity, internal validity, external validity, and statistical validity, to define variable and describe the operational definition of a variable, to describe the different relationships between variables, so positive, negative, curvilinear, and no relationship, to compare and contrast non-experimental and experimental research methods, and to distinguish between an independent variable and a dependent variable, and lastly to discuss the strengths and limitations of laboratory experiments and the advantage of using multiple methods of research. And really what we're going to do is explore some of the basic issues and concepts that are really necessary for understanding the scientific study of behavior. And we're going to focus on the nature of variables and the relationship between those variables. And then, we're going to examine general methods for studying those relationships. And most importantly, we introduce the concept of validity in research, which if you take any other statistical analysis course or a research methods course, really important to understand validity. We're also going to take a look at relationships between variables, whether they're positively associated or negatively associated. And then we're going to look at causation and correlation, which is a really important concept. Okay, so when we look at validity, you are probably aware of what validity is and what the concept is, even if you can't actually precisely, define what it is. And you use the term whether you're asking for information that you found on a website, and whether or not it's valid or not, whether or not it's truthful. And, a juror must decide whether the testimony given in a trial is valid, and someone on a diet may wonder if weight shown on the bathroom scale is also valid. So behavioral scientists, they use the term validity to refer to the extent to which, given everything that is known, a conclusion is reasonably accurate. And that is really the extent to which it approaches what we would call truth. And, should you conclude that the information on the website is true, given what you know about where it comes from, so its source, the evidence that is used to support the claims made on the site? And, when we look at jurors, does the testimony reflect what actually happened? Are there sources of bias or error that lead you to doubt the validity of the testimony that's being given? Or is the scale really showing your actual weight? In some cases, someone is confronted with the information and you need to draw a conclusion about the extent that information is accurate, true, and valid. And so scientists constantly evaluate validity when it comes to their own research and then the research conducted by others. And, are the conclusions made on the basis of the research, is it reasonable? Validity is a key concept in research methods. And so scientific research focuses on several aspects of validity. In this chapter, we're going to look at 4 types. Construct validity, which is the extent to which the measurement or manipulation of a variable, whether it's accurate and it represents the theoretical variable that's being studied or constructed. In the case of measurement, it's the measure that is used to accurately representation of the variable. Internal validity, though, is the accuracy of conclusions that is drawn between cause and effect. External validity is the extent to which a study findings can accurately be generalized to other populations and settings, right? And lastly, statistical validity is the accuracy of the statistical conclusions drawn from the results of a research investigation. And sometimes this is called statistical conclusion validity. And now when it comes to external and internal validity and construct validity, there are other subtypes, and we're going to touch on a few of those.
In this video, we're going to take just a few moments to talk about validity in research. We've already spoken quite a bit about reliability, which is all about the consistency of your measurements, but now we're going to focus on validity, which is more about the accuracy of your measurements. I'm going to talk about 3 different forms of validity in a little bit, but I want to take a step back and just talk a little bit more generally about reliability and validity and where these fit into each other and also into inferential statistics more broadly. So remember, we're headed toward inferential statistics, which is all about using sample data to make conclusions about populations, to answer questions about the world. Reliability and validity are really important for inferential statistics because if you have studies that are not reliable and or not valid, you're going to end up making inaccurate conclusions about the world on the basis of your data, which defeats the whole purpose of what we're trying to do. So I want to talk for a moment about the relationship between reliability and validity. So here's the rule of thumb that you should kind of go by. You can have reliability without validity, but you need reliability for validity. So let me illustrate with an example or two. Here's an example. Let's say I'm a researcher and I'm convinced that thumb size is the best way to measure intelligence. Well, think about this. This would be a pretty reliable sort of measure that we can use, right? Think about test-retest reliability. I can measure your thumb now, and I can measure it a week from now and a month from now, and chances are I'll get the same exact measurement in centimeters or millimeters or whatever every time I measure your thumb. However, do we think that thumb size is a valid, I should say, measure of intelligence? Is it an accurate measure of intelligence? Probably not. So this is an example of a reliable study, but a very invalid one. But now think about the flip side, needing reliability for validity. We've seen an example of this already. If I'm developing an IQ test and you take it tomorrow and you get a 120, and then I give it to you again and you take it and you get a 94, well, this is really unreliable, right? We have very poor test-retest reliability in this case, and as a result, you would probably say this is not a valid measure of intelligence. It's not a valid IQ test because I don't expect that you got 25 points or 30 points or whatever less intelligent over time. So again, you can have reliability without validity, but you need reliability for validity. Okay. So now let's talk about those three different types of validity that I mentioned earlier. First of all, we're going to talk about content validity. Next, we'll talk about criterion validity, and we'll end by talking about construct validity. Notice that all three forms of validity start with C. This is kind of convenient because it makes it easier to remember, but also kind of problematic because it makes it slightly more difficult to differentiate between them, but I'll do my best to help you out in that department. So let's start with content validity. Content validity is used when you want to know whether a sample of items truly reflects an entire universe of possible items in a certain topic. All right, that's pretty wordy, but I can illustrate this very simple idea with an example. Let's say as a professor of statistics, I want to design a test to measure my students' ability in statistics. Pretty reasonable, right? But we need to make sure that this test has good content validity. So let me illustrate. Here's an example of a test that has bad content validity. Question 1, calculate the mean. 2, calculate the mean. 3, calculate the mean, and so on. Think about our definition. This doesn't accurately kind of sample a really representative set of questions that covers the entire content that we're learning about in statistics. Instead, I might want to ask you some things like this on the final exam, for example. Calculate the mean, maybe do a standard deviation, perhaps a correlation, a t-test, some other things, and so on. This is much better. This has higher and greater content validity because I'm doing a better job of covering all the content we learned about in the test. Okay, so next let's talk about criterion validity. Criterion validity is used when you want to assess whether a test reflects a set of abilities in a current or future setting. And there are two types of criterion validity that are really important to know in order to fully understand what criterion validity is all about. First, we have concurrent criterion validity. So think about what concurrent means here. It means here and now, at the same time, etc., etc. So concurrent criterion validity is all about this question here. Does this test accurately assess, again, validity, accuracy, does this test accurately assess my student's current level of ability? So whenever you're given a final exam or you're given a midterm in a class, it's all about concurrent criterion validity. This is what your professors are interested in. If you understand 95% of what we've learned, do you get a 95% on the exam? We would hope that you do, and that would be a good example of solid concurrent criterion validity. A different form of criterion validity, however, is more interested in predicting things about the future. This is called predictive validity. And it's kind of focused on this question here. Does this test accurately assess how my students will do in the future? On the final exam, for example, can I predict how well you're going to do in the future on the basis of this exam that I'm giving you right now? You could think, for example, about SATs and GREs, a lot of these standardized tests that are requirements for, different levels in school that you're trying to enter into. That's what these are all about. We're trying to give you an SAT as an extra method for us to sort of make a best guess about how you're going to do in college. For the GRE, we're giving you, this test to predict how well you're going to do in graduate school. Now, how well these standardized tests actually accomplish this goal is perhaps another issue altogether, another topic of discussion, but for now it's important to just understand that this is the goal behind the tests, to have good predictive validity. So we're going to end by talking about construct validity. I'll note, by the way, that these, three forms of validity are by no means all-inclusive. There are others like face validity, and there's lots of others, but these are by far the most common, I would say. So this is what I'm focusing on here. But before I get to construct validity, I have to take just a second or two to define what a construct is. So in psychology, a construct is a group of interrelated variables that you care about. Think about most things in psychology that you might be interested in measuring. Aggression, for example. Aggression is a complicated thing. There's all sorts of things that make up this construct, this abstract idea of aggression. It might involve your behaviors. It might involve physical behaviors, pushing, shoving. It might involve verbal behaviors, verbal aggression, name calling, insults. There's also relational aggression where, we're talking about manipulating friendships and ruining relationships and things like that. There's all sorts of stuff that goes into aggression. And this is what I mean by interrelated variables. But the overall idea that's kind of behind these interrelated variables is your construct. So construct validity is sort of the truest validity in terms of how we typically think about it. Construct validity is the degree to which your test measures the construct it claims to measure. For example, am I really measuring aggression? And this is so crucial. People argue about this in the field all the time, and when you write a paper, you have to defend the construct validity of what you've done. You have to prove, or at least convince other people as much as possible that, I'm actually measuring the thing that I'm trying to measure, and that's an issue of construct validity. Just as one final note, a way to sort of get at the construct validity is to correlate your scale, for example, or your test or whatever you did to actual outcomes. If you developed an aggression scale that's designed to measure aggression, do you find a correlation between how people do on your scale, how aggressive they appear to be on your scale, and how much aggression they actually show in real life? Can you correlate your scale with real, tangible observations of behaviors? And that's an example of how we might address something like this. In most cases, when we think about validity, it's sort of something conceptual that we're focusing on, and we're just arguing at a sort of theoretical level about whether what we're doing is valid or not. But there are ways like this to sort of put some numbers to this and test it. So in general, again, why do we care about validity and why do we care about reliability? Because it helps us to make accurate conclusions about populations, and that's where we're going to head next. How do we make those conclusions about populations? And it's going to be through a process called hypothesis testing. In this video.
Okay, so that video talks about reliability and validity. So let's just take a look first about reliability. And really, the term reliability in psychological research, it refers to the consistency of a research study or measuring tests. So, for example, if a person weighs himself during the course of a day, they would expect to see similar readings. So scales which measured weight differently each time would be of little use. And the same analogy could be applied to a tape measure, which measures inches differently each time we used it. It would not be considered reliable. So if findings from research are replicated consistently, they are considered reliable. And we're going to talk about this later, but a correlation coefficient can be used to assess the degree of reliability. If a test is reliable, it should show a high positive correlation, meaning when one goes up, the other goes up. And we're going to talk about that a little later in further detail. So if findings from research are replicated consistently, they're considered reliable. Okay, So, of course, it's unlikely that the exact same results will be obtained each time participants and situations, because they vary. But a strong positive correlation between results of the same test indicates reliability. Because, when we sample, when we take a sample of a population, so we look at taking so many students out of an entire university, that's considered the sample. And we did the exact same thing several times. There might be some minor adjustments in the final statistical analysis that we get. But what we're looking for ultimately is a correlation. When one goes up, the other goes up as well. And so, there are different types of reliability. There's internal and external. So internal reliability is the extent to which the measure is consistent within itself. Okay, whereas external reliability is the extent to which a measure varies from one use to another. Okay, and that's really all you need to know right now about reliability. We're going to take further chapters look at that. But when we look at validity, I want you to think of, the concept of validity was first introduced in 1927 by Kelly, and he stated that if a test is valid, if it measures what it claims to measure. So, for example, a test of intelligence should measure intelligence and not something else, let's say such as memory. So a distinction can be made between internal and external validity, and these types of validity are relevant to evaluating the validity of a research study or procedure. Okay, so internal validity refers to whether the effects that you observed in the study are due to the manipulation of the independent variable and not some other factor. Okay, so in other words, there is a causal relationship between the independent and dependent variable. And internal validity can be improved by controlling what we call extraneous variables. And we're going to get into these using standardized instructions or other different or eliminating demand characteristics. So external validity refers to the extent to which the result of the study can be generalized to other settings or other populations over time. Okay, and external validity can be improved by setting experiments in a more natural setting and using random sampling, which is very, very important to select participants. And random sampling really just means that every single person has an equal opportunity of being chosen for the study. And so, that video looked at the different types of validity, content and criterion related validity. Okay. And, content related validity really has two different parts. So face validity, which is, does the test appear to test what it aims to test? And construct validity, does the test relate to the underlying theoretical concepts that it is based upon? Okay. And that's pretty much all you need to know right now about validity. We will go further into that as the class progresses. So when we look at variables, so, really a variable is something that changes. A variable can be a behavior, it can be a thought, a feeling, a situation, a characteristic, or even an event. So anything that varies can be measured is considered a variable. And, any variable must have two or more levels or values. So consider the following example of variables that you might encounter in research or, really in your own life. So as you read a book, you encounter the variable of word length with values defined by the number of letters of each word. And, you can take this one step further and think of the average word length used in paragraphs in the book. And one book you read may use a longer average word length than another. And then when you think about yourself and your friends, you might categorize the people on a variable such as extroversion. Some people can be considered relatively low on the extroversion's variable, considered introverted. Others are high on extroversion. And you might volunteer at an assisted living facility and notice that the residents differ in their subjective well-being. And, some of the people seem much more satisfied with their lives than others. And, when you're driving your car in front of you, and the car in front of you brakes or slows down, the period of time before you apply the brakes in your own car is considered a response time. That would be a variable. Okay, so examples of variables, a psychologist might study include, cognitive task performance, depression, intelligence, reaction time, rate of forgetting, aggression, gender, eye color, marital status. These are all considered variables. Okay, so, a variable such as aggression or cognitive task performance or pain or self-esteem or even word length must be defined in terms of the specific methods used to measure or manipulate it. So the operational definition of a variable is a set of procedures used when you measure or manipulate the variable. So a variable must have an operational definition to be studied empirically. Okay, the variable given in your textbook of bowling skill could be operationalized as a person's average bowling score over the last 20 games, or it could be operationalized as the number of pins that fall in a single row. So such a variable is concrete and easily operationalized in terms of score and then the number of pins. But things become more complicated when studying behavior. So for example, a variable such as pain is very general and more abstract. And really pain is a subjective state that can't always be observed. But that does not mean that we can't create measures that then will infer how much pain someone is experiencing. Okay, so a common pain measurement in both clinical and research settings is the McGill Pain Questionnaire. And it has both long and short form. And the short form includes a 0 to 5 scale. We'll look at that. It's called a Likert scale, with descriptors of no pain, mild, discomforting, distressing, horrible, and excruciating. And there is also a line with endpoints of no pain and worst pain, possible pain, and the person responding by making a mark at the appropriate place on the line. And so additionally, the questionnaire offers sensory descriptors such as throbbing, shooting, stabbing, and each of these descriptors has a rating of none, mild, moderate, and severe. So this is a relatively complex set of questions, and it's targeted for use with adults. And really what we're looking at is they've really operationalized pain there, right? And so when somebody says marks a 2 on the scale and they state that it is mild, that gives us, a measurement and understanding of how they've decided to operationalize pain. So, there are 2 important benefits in operationalizing and defining a variable. First, the task of developing an operational definition of a variable, it forces the scientist to discuss abstract concepts in concrete terms. And that process can result in the realization that the variable is maybe too vague for the study. Maybe they need to define it a little bit more. And this realization does not necessarily indicate that the concept is meaningless. It just means that the systematic research is not possible until the concept can be operationally defined. Okay? So in addition, operational definitions help researchers communicate their ideas to others. So if someone wishes to talk about aggression, I need to know exactly what is meant by this term, because there are many ways of operationally defining it. So, for example, aggression could be defined as the number of duration of shocks delivered to another person, or it could be the number of times a child punches an inflated toy clown, or it could be the number of times a child fights with other children during recess, or it could be the homicide statistics gathered from police records, so on and so forth. So communication with another person will be easier if we agree on what exactly is meant when we use the term aggression in the context of the research that you're going to conduct. So, there are important questions that arise once a variable is operationally defined. How good is the operational definition? How well does it match up with reality? How well does the average bowling score really represent the skill of the individual being measured? And that's when we look at construct validity. In construct validity, it refers to the accuracy of our operational definitions. So, does the operational definition of a variable actually reflect the true theoretical meaning of the variable? And if you wished to scientifically study the variable, let's say extroversion, you need some way to measure extroversion. And so psychologists, they develop measures that ask people whether they like to socialize with strangers or whether they prefer to avoid such situations. So, do the answers on such a measure provide a good or true indication of the underlying variable of extroversion? So if you're studying anger, will telling college students that judges have rated them unattractive create feelings of anger? Researchers are then able to address these questions when they design their studies and examine results. Okay, so, many studies investigate the relationship between two variables. So, do the levels of two variables vary together? So, for example, does playing violent video games result in greater aggressiveness? Example, is a speaker's perceived credibility related to how fast she or he talks? Or as age increases, does well-being increase as well? So remember that some variables have true numeric values, whereas the level of other variables are simply different categories. So female versus male, being a student athlete versus a non-student athlete. Okay, so for the purpose of describing relationships among variables, we're then going to be discussing relationships in which both variables have true numeric properties. So when both variables have values along a numeric scale, many different shapes can describe these relationships. Okay, so we're going to look at the four most common relationships found in research: the positive linear relationship, the negative linear relationship, and the curvilinear relationship. Okay, and of course there are situations in which there is no relationship whatsoever between the variables. And so really when we look at a positive linear relationship, what we're saying is that the increases in the first variable are accompanied by an increase in the second variable. So let's say we're studying grades, and we look at the variables of how long somebody is studying. So a positive linear relationship would mean the more someone studies, the better mark they get, right? As one goes up, the other goes up. When it comes to a negative linear relationship, increases in the first variable are accompanied by a decrease in the second variable. So in that studying, let's say we measured somebody's sleep. Less sleep equals, more sleep equals a better grade. Okay, so increases in the first variable are accompanied by decreases in the second variable. And then a curvilinear relationship. So changes in the first variable are accompanied by both increases and decreases in another variable. Okay, and then obviously there's no relationship. And this can be seen by this chart here. So, when we look at, this is looking at graph A, it's looking at positive linear relationship here, and it's attitude change and speech rate, right? So, as attitude goes up, speech rate goes up. And you can see it's a positive relationship. In graph B, a negative linear relationship. So the amount of noise, as the amount of noise goes down, the group size gets bigger. Okay. A curvilinear relationship is liking for stimulus and the complexity of visual stimuli. You can see that it goes up and then it can go down depending on an increase in one of the variables. And then obviously a no relationship is just a flat line because, it doesn't increase or decrease at all.
First, let's consider some... Hello, I'm Paul Henney, and I'm a philosophy graduate student at Duke University. And in this video, I'm going to talk to you about correlation and causation. Maria and Andy are high school students in Arizona. Andy always gets an A on his math test when it's sunny outside. On one sunny day, before Andy goes to math class, he tells Maria, "I'm going to ace this test today because it's sunny." Maria objects. "No, Andy, you'll not ace this test because it's sunny. You'll ace this test because you studied. The fact that it's sunny outside has nothing to do with it." Andy responds, "But Maria, I always ace my tests when it's sunny." Maria replies, "Okay, sure, but that's just because you always study for your math tests, and it's always sunny here in Arizona. The sunniness does not cause you to ace the test." Maria's correct. Andy's making a mistake, right? The sunniness doesn't cause Andy to ace his test. The two events, the sunniness and Andy acing his test, occurred together without one causing the other. In other words, the two events are correlated in some way, but there's no causal relation between them. Andy's reasoning here is fallacious, simply because two events are correlated does not mean that one caused the other. This conflation of correlation and causation is what we will talk about in this video. First, let's consider some other examples. Fido barks when his tail wags. People with higher grades in college have higher grades in high school. People who take vitamin C recover more quickly from a cold. These are correlations. That is, there's a correspondence between these events. For example, the dog, Fido, barks when his tail wags. But there's no reason to suspect that there's a causal relation between these events. While these events often occur together, there are many times when Fido's tail wags and he doesn't bark, and there are times when Fido barks but doesn't wag his tail. Furthermore, we may suspect that there is some common cause for these events, like Fido's excitement when his owner comes home. Now that we can agree that these are cases of correlation without causation, we can discuss two types of correlation, positive and negative. In the next video, we'll discuss how these types of correlation specifically relate to different types of causation. But for now, let's just introduce them. When events frequently occur together, like in the examples above, they are positively correlated. If two events are positively correlated, then when one event is present, the other is often present as well. In our first example, it being a sunny day in Arizona is positively correlated with Andy succeeding on his math test. On the other hand, two states are negatively correlated when it's likely that when one event occurs, the other will not occur. For instance, when it snows, it's often not very sunny. So snowing and sunniness are negatively correlated. We often hear about positive and negative correlations, especially in the news. Headlines like, "Taking vitamin C helps you recover more quickly from a cold," indicate positive correlations. Taking vitamin C is positively correlated with recovering from the common cold more quickly than if one had not taken vitamin C. Or headlines like, "Eating more nuts makes you less likely to have higher levels of bad cholesterol," indicates that eating more nuts is negatively correlated with having higher levels of bad cholesterol. You may have heard headlines like these and had conversations with some friends about them. And you may have heard someone say something like, "Awesome, so I'll just eat more nuts and get rid of my bad cholesterol." You may have also had the experience of someone else saying, "Yeah, but that's just correlation, not causation." Of course, this person may just be a jerk, but they are right to point this out. Unless you had evidence that a causal relation held, it is a mistake to suggest that this correlation is actually a causal relation. So it'd be wrong to say that eating more nuts will cause you to have lower levels of bad cholesterol, unless you had evidence that the causal relation held. So let's consider an example where two events are positively correlated when neither causes the other. Consider this again. People with higher grades in college have higher grades in high school. Here, earning higher grades in college is positively correlated with earning higher grades in high school. Now, it's incorrect, as we've discussed, to claim that earning high grades in high school always causes someone to earn high grades in college. Nonetheless, earning high grades in high school may sometimes cause a person to earn high grades in college. For example, Jane may have gotten good grades during high school, and some of those grades transferred to her college, which causes her success in college. Here, success in high school for Jane causes her success in college. But most of the time, it is not the success in high school that causes success in college. It is usually someone's working hard in college courses that causes that person to succeed in college. And at that type level of the statement, where we are identifying a correspondence of two data sets, the causal claim is false. So again, the two events, high school success and college success, are positively correlated, but they do not cause one another. When two events are correlated, it may seem that one causes the other, but there may be alternative explanations we've ignored, like working hard in college courses causes that person's overall success in college. So it's fallacious to conclude from only the fact that two states are positively or negatively correlated that one causes the other, because there may be another cause that explains the outcome. It may be that there's a common cause for both of the events, or that there's an alternative cause altogether. On the other hand, the correlation might just simply be a coincidence. But this explanation and other questions will have to wait for part 2, where we will talk more about the analysis of causation and how it relates to different types of correlation. If you're interested in these false cause fallacies, you may also want to check out our video on the post hoc fallacy. Thank you for watching.
Okay, so that's a really good video on causation and correlation. And the reason I brought it up, it's not in your textbook yet. I think we look at it later on in the semester. But it's really, really important because a lot of times we say, oh, one thing equals another, or every time this happens, this happens. And we tend to create this fallacy that one causes the other. And statistics and in psychological studies, we never ever say that. It's very rare that we'll say one causes the other. Okay. We will say there's a correlation, where one thing potentially is related to another. But one causing another is not used very often in studies. I just want to take another look at these graphs here. Because I think this is where students typically get a little confused around the differences. And I want to go over them again. So really, in a positive relationship, an increase that we're seeing, this is graph A, an increase in the value of one variable is accompanied by an increase in the value of the second variable. Okay, so when we think of rate of speech in this specific graph, and we think of, the variable, the rate of speech when delivering a persuasive message. So are fast talkers more persuasive? And research suggests that the answer is actually yes. In Smith and Schaefer studies, students listen to a speech delivered at a slow, it's about 144 words per minute, intermediate, 162 words per minute, and fast, 214 words per minute speech rate. The speaker advocated a position favoring legislation to raise the legal drinking age, and the students initially disagreed with this position. So in graph A, figure 1 shows the positive linear relationship between speech rate and attitude change that was found in the study. So that is the rate of speech, as rate of speech increased, attitude also increased as well, the attitude change. So in a graph like this, we see a horizontal and vertical axis termed the x-axis and the y-axis, respectively. And so values of the first variable are placed on the horizontal axis, labeled from low to high, and values on the second variable are placed on the vertical axis. Graph A shows that higher speech rates are associated with greater amounts of attitude change. So negative linear relationship. So variables can also be negatively related. So in a negative linear relationship, an increase in the value of one variable is accompanied by the decrease in the value of another variable. Okay. So Lentane et al. Were intrigued with reports that increasing the number of people working on a task may actually reduce group effort and productivity. And so the researchers designed an experiment to study this phenomenon. And so they termed the idea of what they called social loafing, which you may have observed in group projects. The researchers asked participants to clap and shout to make as much noise as possible. And they did this alone or in groups of 2, 4, or 6 people. So in figure 1, graph B, it illustrated the negative relationship between number of people in the group and the amount of noise made by each person. So as the size of the group increased, the amount of noise made by each individual decreased. The two variables are systematically related, just in a positive relationship. Only the direction of the relationship is reversed. Okay. Now this one is a little more difficult. In a curvilinear relationship, increases in the values of one variable are accompanied by a systematic increase and decrease in the values of the other variable. So in other words, the direction of the relationship changes at least once. And this type of relationship is sometimes referred to as a nomatonic function as opposed to a monotonic function like a positive or negative relationship, a relationship that does not change direction. So in graph C, figure 1, it shows a curvilinear relationship. This particular relationship is called an inverted U. So a number of inverted U relationships are described by Grant and Schwartz. So graph C depicts the relationship between the complexity of a visual stimulus and liking of that stimulus. So having a complex visual stimulus, one with a lot of detail, is associated with more visual attractiveness, but only up to a point. So too many details, and then the relationship becomes negative as visual attractiveness diminishes. So of course it is also possible to have a U-shaped relationship. Research on the relationship between age and happiness indicates that adults in their 40s are less happy than younger or older adults. So a U-shaped curve results in this relationship, and it is graphed here. And then, obviously no relationship. Really, when there is no relationship between the two variables, the graph is simply a flat line. And the figure 1 here in graph D illustrates that. That the relationship here specifically is the relationship between crowding and task performance found in a series of studies that by Friedman et al. So unrelated variables vary independently from another. And increases in crowd were not associated with any particular changes in performance. Thus, a flat line describes the lack of relationship of the two variables. And you rarely hear about variables that are not related. So in large US studies, such as the General Social Survey, the size of the community in which a person lives is not related to reported health problems or amount of internet use. Total flat line. Okay. Okay, so remember that, those relationships between variables, they are general patterns. And even if, in general, a positive linear relationship exists, it doesn't necessarily mean that everyone who scores high on the one variable will also score high on the second variable. So there are individual differences or individual deviations from the pattern. So, in addition to knowing the types of relationships between two variables, it's also necessary to show the strength, how strong that relationship is. So we need to know the size of the correlation, how much oomph it has between the variables. And sometimes two variables are strongly related to each other and show little deviation from the general pattern. And other times, two variables are not highly correlated because many individuals, they deviated from that general pattern. And so a numerical index of the strength of relationship between variables is called a correlation coefficient. So correlation coefficients are very important because you need to know how strong the variables are related to another, right? And correlational coefficients are going to be discussed further in, when we look at actual correlation later on.
The correlation coefficient doesn't just tell us whether two variables move in the same or opposite direction like the covariance does. It also indicates how strong the relationship is, and its value ranges from -1 to 1. As such, A, 1 indicates the strongest possible positive correlation. Think of it as perfect direct proportionality. If I pay you $2 for every apple you pick, the correlation coefficient between the number of apples you've picked and your apple picking earnings for that day will be 1. B, -1 indicates the strongest possible inverse correlation, or, if you will, perfect inverse proportionality. To use the previous example, if I start the day with a large pile of money from which I pay you, the correlation coefficient between the number of apples you've picked and the amount of money in my pile will be -1. And C, 0 indicates that there's no correlation at all. Formula-wise, the most popular one is the Pearson correlation coefficient, which is represented by the letter R and calculated by dividing the covariance by the standard deviation of one variable multiplied by the standard deviation of the other. Simply 1. Watch our video about the covariance. 2. Watch our video about the standard deviation. The correlation coefficient.
So really what you need to know from that video is that typically we use Pearson, and really it's going to, the R value or the correlation coefficient is going to go from +1 to -1. +1, the closer you get to 1 in a positive, it's going to be a strong relationship. The closer you get to 0 will be like a weak positive correlation. And then when you start getting to negative, the lower negative number will be a weak negative relationship. And as soon as you get to -1, closer to -1, it's a very strong but inverse or negative relationship. Okay. So, when we detect a relationship between variables, we reduce the uncertainty by increasing our understanding of the variables that we are examining. So the term uncertainty implies that there is some randomness in events. And, scientists refer to this as random variability in events that occur. And, research can reduce random variability by identifying systematic relationships between variables. So, in identifying relationships between variables, it seems complex, but it's actually fairly simple. For this example, the variables will have no quantitative properties, and we will not describe increases in the values of variables, but only differences in the values. And in this case, whether a person is an active user, let's say, of Instagram. So, the textbook says, suppose a researcher has permission to ask 200 teens in your town whether they use Instagram frequently. Now, suppose 104 of them said yes, and the remaining 96 said no. What do you then do with that information? You know that there is variability because there's some differences in people's use of Instagram. Some people are more frequent users and some are not. And so this variability is called random variability. If you tried to guess if a teen was a user of Instagram, you would have to make a random guess. And you would be right half of the time and wrong half of the time, because we know that about 50% of the teens are users and 50% are not. Any guess you make will be right about half the time. But if we could explain the variability, it wouldn't actually be so random anymore. And so how can the random variability be reduced? And the answer is to see if we can identify variables that are related to Instagram use. So, let's suppose a researcher also introduced a question, when it comes to gender related, with space to write an answer on gender. So do you most identify as male, female, or other? Now let's look at what happens when you examine whether gender is related to then Instagram use. And so table 1 here shows the one possible outcome. To simplify, only those indicating male or female are included. Not that there are 100 males or 100 females in the study. The important thing, though, is that 44 of the males say they frequently use Instagram compared to 61 females. So now we have reduced the random variability we then clearly have. And before you had that information, there would be no way of predicting whether a given person would be a regular Instagram user. Now that you have the research findings, you then can predict the likelihood that a female would use Instagram and any male would not use it. Now you will be right about 60% of the time. And that's a big increase from 50% when everything was random. And so you have to ask yourself, is there still random variability? And the answer is clearly in this case, yes, because you're going to be wrong about 40% of the time if you don't know when you will be wrong. And for unknown reasons, many males will say that they are frequent users of Instagram and many females will not. Can you reduce this remaining uncertainty? And the request to do so would require more information, more additional research. And with further studies, you then might be able to identify other variables that are related to Instagram. For example, variables such as income or extroversion may also be related to Instagram use. So the discussion underscores once again that relationships between variables are rarely perfect. There are going to be males and females who do not fit the general pattern. Okay. So, the question then becomes, how can we determine whether variables are then related? And there are two general approaches to the study of relationships among variables. There's a non-experimental method and the experimental method. And the non-experimental method really is relationships are studied by observing variables of interest. And this can be done by asking people to describe their behavior directly or observing their behavior, or let's say recording physiological responses, or even examining various public records like census data. In all these cases, the variables are observed as they occur naturally. Okay, relationship between the variables is established when the two variables vary together. Okay, so for example, the relationship between class attendance and course grades can be investigated by obtaining measures of these variables in college classes. A review of many studies that did this concluded that attendance is indeed related to grades. Now, the second approach is considered the experimental method, and it involves directly, and this is the important part, involves directly manipulating or controlling of a variable. So, the research manipulates the first variable of interest and then observes what happens, the response. So, example, Ramirez and Bilioc in 2011 were interested in the anxiety produced by important high-stake examinations. And because such anxiety may impair performance, it is important to find ways to reduce that anxiety. So in the research, they tested the hypothesis that writing about testing worries would improve performance on the exam. Okay, so in their study, they used this high stakes test. Students were led to believe that the monetary payout to them and themselves and their partner was dependent on their performance. So the writing variable was then manipulated. Some students spent 10 minutes before taking the test writing about what they were thinking and feeling about the test, and the other students constituted a control group. And these students simply sat quiet for 10 minutes prior to taking the test. Next, the new important test was then administered. The researchers found that students in the writing condition improved their scores. Those who actually wrote about their anxiety or their stress did better. The control group's scores actually decreased, right? So again, we are manipulating and controlling. We're controlling a variable here with a control group. That's how you know it is considered the experimental method. So in a non-experimental method, suppose a researcher is interested in the relationship between, let's say, exercise and anxiety. How could that topic be studied? So again, the non-experimental method is also known as the correlational method because it allows us to observe covariation between variables. But this method is not ideal when we ask questions about cause and effect. And it can be difficult to tell the direction of the cause and effect of which variable affects the other. And then researchers then face the third variable problem, the possibility that there could be what we call extraneous variables or confounding variables that could actually be responsible for what we observed or the difference.
Okay, by now you should be familiar with the procedure and vocabulary involved in an experiment. Terms such as trial, random assignment, control group, experimental group, and independent and dependent variables should be second nature to you. And you should be aware that an experiment is designed to determine the effect of an independent variable on a dependent variable. See Difficult Topics video, Experimental Design. Now, in a perfect experiment, only the independent variable would have any effect on the dependent variable. But alas, life and experiments are rarely perfect. Extraneous variables are often present in an experiment and may or may not compromise the validity of the experiment. An extraneous variable that affects the validity of an experiment is referred to as a confounding variable. Now, to better understand what I mean, let's take an experiment that's been done in grade schools for generations. Let's see whether sunlight makes plants grow. You start your light growth experiment by placing one plant in the sunlight and one in the darkness, and then you wait. When you see that one of your plants is doing better than the other, you automatically assume that it's due to the sunlight, but you may be wrong. Did you accurately measure the water given to each? Or how about the soil and air temperature, or the size of the containers, and even the location? These are all extraneous variables, extra variables that may or may not interfere with your experiment. Now, if any of these extraneous variables impact your results, then we call it a confounding variable. Think of all the extraneous and confounding variables that may be present in a psychological experiment, especially those involving humans. Then you'll get an idea of why it's so important to recognize extraneous variables, especially the confounding ones. Okay, by now you should be familiar with the procedure and vocabulary involved in an experiment. Terms such as trial, random assignment, control group, experimental group, and independent and dependent variables should be.
Okay, so when we look at the non-experimental method, so suppose a researcher is interested in the relationship between exercise and anxiety. How could this topic be studied? And so using the non-experimental method, the researcher then could devise operational definitions to measure the amount of exercise and that people engage in and then their level of anxiety. And there could be a variety of ways of operationally defining either of these variables. So for example, the researcher might simply ask people to provide self-reports of their exercise pattern and current anxiety level. Now then, suppose that the researcher collects data on exercise and anxiety from a number of people and finds that exercise is negatively related to anxiety. That is, people who exercise more have lower levels of anxiety. So the two variables covary or correlate with each other. So observed differences in exercise are associated with the amount of anxiety. And so because a non-experimental method allows us to observe covariation between variables, another term that is frequently used to describe this procedure is the correlational method. And within this method, we examine whether the variables correlate or vary together. So the non-experimental method seems to be a reasonable approach to the study of relationships between variables such as relationship and anxiety. That relationship is established by finding that the two variables vary together. But we know the two variables are related, but what can we say about the causal impact of one variable on another? Right? There are two problems with making causal statements when the non-experimental method is used. One, it can be difficult to determine the direction of cause and effect, and two, researchers face a third variable problem. That is, extraneous variables may be causing the observed relationship. And so the problem is illustrated here in figure 2. The arrow linking variables depicts the direction of causation. Right? Exercise causing anxiety reduction, or anxiety causes a reduction in exercise. We don't know which way the direction of the causal effect is. And then the third variable problem, higher income leads to both lower anxiety and more exercise. It could be a third variable of income that is directly impacting the amount of exercise and the amount of anxiety. So the directionality problem and the third variable problem are two issues when using the non-experimental method.
Imagine that each of these 3 cups contain the same bottled water. The only difference between them is that orange, green, and yellow food coloring was added to change their appearance. A psychologist is investigating the research question, does the color of a drink affect the taste? If you think so, how would a psychologist even go about answering this question? The answer? Conduct an experiment. In this Psychedemia episode, I covered the experimental method, psychologists' most powerful research tool. Because this research question requires a psychologist to look at causal relationship between variables, in this case does color cause a change in taste, they must perform an experiment. And only the experimental method can establish that changes in one variable lead to changes in another. In a simple experiment, a researcher manipulates a variable like color to determine its effect. To begin an experiment, a psychologist must identify his or her variables. A variable is anything that can vary or change, in this case both color and taste. There are 2 primary types of variables, independent variable and dependent variable. The independent variable is the treatment variable that is manipulated by the psychologist. It represents the causes of some outcome. In this case, the psychologist is only manipulating the color to see if it affects the taste. On the other hand, the dependent variable represents the outcome that the psychologist is measuring. This will be the data that is collected and analyzed. In this case, the response or outcome is taste. Before I move on, check your understanding of both types of variables. The research question is, does money increase happiness? Pause the video here and identify the independent variable and dependent variable in this scenario. How'd you do? The independent variable is the amount of money. Money represents the treatment to see if it affects the outcome. The psychologist can manipulate the amount of money among participants. The dependent variable is a level of happiness. Remember, the dependent variable represents the outcome or response. The psychologist has no influence on the level of happiness among participants. It is also very important in experimental research to clearly define the variables. This is one of the most significant yet confusing concepts for students. Defining the variables in an experiment is known as operationalizing. The purpose of operationalizing is so that another psychologist could clearly replicate or copy the same study. Let's practice operationalizing variables. Take a look at this research question. Does lack of sleep impair memory? A psychologist must clearly define the variables sleep and memory into something that can be studied and measured. I have defined sleep as sleeping less than 3 hours per night and defined memory as memorizing a list of 20 random numbers in order. Without defining the variables, no one would know how a psychologist investigated this particular research question. Take a moment here and pause the video and operationalize these concepts: aggression, health, and sadness. Remember, define them clearly so that another psychologist knows exactly what you did. Now that I've covered fundamental vocabulary, let's begin designing an experiment. A psychologist must first randomly assign participants to either the group that receives the treatment, this group is exposed to the independent variable, or the group that receives no treatment. This is the control group that may receive a placebo, for instance. The control group acts like a comparison group. This is important because without the control group, a psychologist cannot tell whether the treatment is what is causing a change. To study the particular research question, does the color of a drink affect the taste? Participants in the control group receive normal bottled water with no flavoring or coloring. Participants in the experimental groups also receive normal bottled water. However, there is food coloring added to their glasses to create a drink that appears orange, green, and yellow. This is the treatment. A psychologist, for example, might hypothesize that participants in the experimental groups will pick up hints of orange, lime, and lemon flavors because of the food coloring. Don't forget that a psychologist must also operationalize the variables and make them measurable. For example, how can taste be measured? A psychologist might use a survey. Participants in both groups receive a Likert survey, measuring the drink's sweetness, how refreshing it is, and level of carbonation. This way, a psychologist can collect data on taste and compare the responses of the control group and experimental groups. After all the participants finish their drinks and take the survey, the data is then collected and analyzed to look for variations. Our experiment is complete. It is important to note that all variables in an experiment must remain the same. For example, temperature of the water, type of drinking glass, instructions to the participants, except for the independent variable. A good researcher knows that many other factors besides the independent variable can influence the results of the experiment. These are known as confounding variables, and there are many types. One example is experimenter bias, when researchers unconsciously treat participants in the experimental and control groups differently to increase the chance that they confirm their hypothesis. Demand characteristics are cues a researcher might hint to participants about the purpose of the study. Participants might even change their behavior just because they're being observed in a study. This is known as the Hawthorne effect. One way to eliminate confounding variables, which I discussed earlier, is randomly assigning participants to the experimental and control groups. This is called random assignment. This is like flipping a coin, where each participant has an equal chance to be in each group. Another way is to use a single-blind procedure, where participants are unaware of which group they are assigned to, or a double-blind procedure, where both participants and the researcher are unaware.
Okay, so we look at the experimental method. The experimental method reduces ambiguity and thus uncertainty in the interpretation of results. So with the experimental method, one variable is manipulated and the other is then measured. And the manipulated variable is called the independent variable. And the variable that is measured is termed the dependent variable. So in an experiment, all extraneous variables are controlled by being held constant. So this is called the experimental control. So the experimental control is where extraneous variables are controlled by making sure every feature of the environment except the manipulated variable is then constant. Okay. In other words, any variable that is held constant cannot then become a confounding variable. Now, randomization, which is really any variable that cannot be held constant, is controlled by making sure that the effects of the variable are random. So the experimental method eliminates the influence of such variables by randomization. And randomization ensures that an extraneous variable is just as likely to be affected to affect one experimental group as it is to affect the other group. And to eliminate the influence of individual characteristics, the researcher assigns participants to two groups in a random fashion.
Randomization, or random assignment, provides a way of eliminating all possible systematic differences between conditions all at once. Think of the relation between violent imagery and aggression. Suppose I encourage a group of children to play a violent video game, say GTA 5, for a total of 10 hours in 1 week, and I deny another group any access to violent imagery for the same period of time. Suppose I find that children who played the violent game are more aggressive than the control group. Of course, there are still many possible alternative explanations for the difference in aggressive behavior, other than violent stimuli. Suppose children could volunteer for the violent gameplay condition. It would not be hard to imagine that this group would consist of more boys, or children more drawn to violence and aggression than the control group. Such systematic differences between the groups, providing alternative explanations for more aggressiveness in the experimental group, would likely have been prevented with random assignment. Okay, let's see why. I could have randomly assigned children to the conditions by flipping a coin. Heads for the experimental condition, tails for the control condition. A naturally aggressive child would have a 50-50 chance of ending up in the experimental condition. The same goes for a child of the male sex, a very meek child, a child with impaired eyesight, a child with large feet. Any property you can think of, a child with that particular property will have an equal chance of being assigned to one of the conditions. Put another way, how many boys do we expect in the experimental condition? About half of all boys in the study, because for the boys, on average, the coin will show heads half of the time. How many naturally aggressive children will end up in the experimental condition? Again, about the same number as in the control condition. And the same goes for all other characteristics we can think of. On average, randomization ensures that there is no systematic difference between the groups other than on the independent variable. Of course, in any one particular study, it is possible, entirely due to chance, that we end up, for example, with more girls in the control group, possibly explaining why this group is less aggressive. I call this a randomization error. We rely on the law of large numbers when we flip the coin, but this law doesn't always work out, especially in small groups. Suppose there are only 4 boys and 4 girls to assign to the 2 groups. It's not hard to imagine that the coin toss will come out something like this. First girl, heads. Second girl, tails. First boy, heads. Second boy, heads. Third boy, heads. Third girl, heads. Fourth girl, tails. Fourth boy, tails. The experimental group now consists of 3 boys and 2 girls, 5 children in all. The control group consists of 1 boy and 2 girls, 3 children in all. The problem is that the groups are not of equal size, which is a nuisance, statistically speaking. We also have a systematic difference in terms of sex. One solution is to perform a randomization check. We can measure relevant background or control variables and simply check to see whether randomization worked and the conditions are the same, or whether randomization failed and the conditions differ on these variables. There is a way to guarantee randomization works on a select set of variables using restricted randomization procedures. Blocking is the simplest form of restricted randomization. It ensures equal or almost equal group sizes. We pair children up in blocks of 2 and flip a coin to determine where the first child goes. The second child is automatically assigned to the other condition. Repeat for all children, and if we have an equal number of participants, equal group sizes are ensured. In stratified restricted random assignment, we use the blocks to ensure not just equal numbers, but also equal representation of a specific subject characteristic. For example, equal numbers of boys and girls in each group. We can arrange this by first pairing up all the girls, and for each block of girls, flipping a coin to determine to what condition the first girl is assigned. We then automatically assign the second girl to the other condition. We now have a girl in each condition. We do the same for the second block of girls, end up with 2 girls in each condition. The same method is applied in assigning the boys, so that we end up with 2 boys and 2 girls in each condition. Of course, stratified randomization has its limits. You can apply it to several characteristics combined, sex and age, for example, but with more than 2 or 3 variables to stratify on, things become complicated. Moreover, there's an endless number of subject characteristics. It's impossible to control them all. I have one final remark about randomization in repeated measures designs, concerning within subjects designs, where all subjects are exposed to all of the conditions. In this case, randomization might seem unnecessary, but this is not the case. If all subjects are exposed to the conditions in the same order, then any effect could be explained by maturation, or some sort of habituation effect that spills over from one condition to the other. So in within subjects designs, the order in which subjects are exposed to the conditions should be randomized. We call this counterbalancing. Subjects are assigned to one out of all possible orderings of the conditions, possibly using blocking to ensure that no one ordering is overrepresented.
Okay. So you can see how there are different types of randomization and how important it is in order to make sure that every single person has an equal opportunity of being either selected to the experimental group or the control group. Okay, so internal validity is the ability to draw conclusions about causal relationships from the results of a study. So a study has high internal validity when strong inferences can be made that one variable causes changes in another variable. And one can see strong causal inferences, that can be made more easily when the experimental method is then used. So strong internal validity requires that there must be temporal precedence. And really what that means is the causal variable should come first in the temporal order of events and be followed by the effect. So the experimental method addresses temporal order by first manipulating the independent variable and then observing whether it has an effect on the dependent variable. In other situations, you may observe the temporal order, or you may logically conclude that one order is more plausible than another. The second, requirement for internal validity is covariation. There must be covariation with the two variables. Covariation is demonstrated when the experimental method, when the participants is in an experimental condition or an exercise condition, shows the effect, such as a reduction in anxiety, whereas participants in a controlled condition, no exercise, they do not show this effect. And lastly, eliminate plausibility or alternative explanations. There is a need to eliminate plausible alternative explanations for the observed relationship. An alternative explanation is based really on the possibility that there is some confounding third variable that is responsible for the relationship that we're observing. So when we design research, a great deal of attention is then paid to eliminating alternative explanations. And because by doing so brings us closer to the truth. So eliminating alternative explanations is fundamental to internal validity. The experimental method begins by attempting to keep such variables constant through random assignment and through experimental controls. So, when the relationship between variables is studied, researchers generally conceptualize them as having a cause and effect relationship. Okay. And so researchers use the term independent variable and dependent variable when referring to the variables being studied. In an experiment, the manipulated variable is the independent variable. So after manipulating the independent variable, the researchers measure a second variable called the dependent variable. And the basic idea is that the researchers make changes in the independent variable and then see if the dependent variable changes in response. And so the variable that is considered to be the cause is called the independent variable, and the variable that is the effect is called the dependent variable. So the researcher manipulates the independent variable and then measures the resulting change in the independent variable. So unlike the real world, experiments are tightly controlled. Okay, so the external validity of a study is the extent to which the results can be generalized to other populations and settings. So another alternative is to try to conduct an experiment in a field setting. So in a field experiment, the independent variables manipulated in a natural setting, and they are more realistic, more generalizable to the population, but they offer less controls. And some variables cannot be or should not be manipulated. Okay, so sometimes the experimental method is not feasible It's not a feasible alternative because experimentation would be either unethical or impractical. For example, child rearing practices would be impractically manipulated with the experimental world. And participant variables are characteristics of an individual that cannot be manipulated, such as age, right? Some questions are not answered by an experiment. So a major goal of science is to provide an accurate description of events. That's the goal of much research, is to describe behavior. Okay. In those cases, causal inferences are not relevant to the primary goals of the research. A class example of descriptive research in psychological means comes from the work of John Piaget, who observes the behavior of his own children as they matured. So in many real-life situations, a major concern is to make a successful prediction about a person's future behavior. For example, success in school, or ability to learn a new job, or probable interest in various major fields in college. In such circumstances, there may be no need to be concerned about issues of cause and effect. It is possible to design measures that increase the accuracy of predicting future behavior. And so, validity refers to the idea that given everything that is known, a conclusion is reasonably accurate. So validity refers to, again, to the truth, and that accuracy represents representation of information. And research can be described and evaluated in terms of, remember, the 4 types of validity. Construct validity refers to the extent to which measurement or manipulation of a variable accurately represents the theoretical variable being studied. Internal validity refers to the accuracy of conclusions drawn about cause and effect. External validity, which is the extent to which findings of a study can accurately be generalized to other populations and settings. And statistical validity is the accuracy of the statistical conclusion drawn from the results of an investigation.